Hello. Today we're gonna talk about addition, and composition of vectors. So, what is addition and what is composition? I think addition is pretty clear, and composition actually refers to combining multiple things to be represented by a single thing. So it's basically like addition, but it's not always addition. It might include subtraction and other operations as well. So that we will learn in vector addition, vector subtraction, and much more. So now let's talk about why do we say composition of vectors as well. To understand this, we must talk about vectors. So don't follow vectors don't follow the ordinary ordinary law of algebra. So this is the key point that gives us trouble. And why does it not follow the law of algebra? Due to their direction. So it's due to their direction that causes the trouble. So they are added they are added geometrically geometrically or vectorially. So in order to do addition, subtraction, or any operation in vectors, you must use vector algebra. So when we are talking about doing it vectorially, so another point that I'm going to add is we can only add like vectors. So we will talk about what like vectors are. And finally, let's talk about the definition of this term. So this term is it is the process of adding two or more vectors into a single vector which is actually known as a resultant. So let's change the color so that we know that this is something important. So this is an important term which is resultant. So you represent it in a resultant. So now before we talk about something else, let's talk about what does it mean that it does not follow the law of algebra, and what does it mean that it is added geometrically or vectorially, and what does it mean that we can only add like vectors. And I think the definition is pretty clear. It's just combining multiple vectors into a single vector, which is also known as a resultant. That is addition and composition of vectors. We are saying addition because in a sense you're always doing addition, but it's not the addition like in math. It's kind of like combining. We are trying to say even this addition that I wrote is written in terms of combining rather than adding. Okay, so let's look at some examples. So let's take a look at some examples. Let's look at normal algebra and let's look at vectors. So suppose I had 1 kilogram and I added another kilogram to it. It will always be, no matter what I do, it will always be 2 kilograms. So this is algebra. So we are adding units, and even though if we didn't add units, so which means I could express this as 1, like this: 1 plus 1 equals 2, and this will always be true. So this is always true. But if I have a vector, suppose I will say vector 1, and I add it to vector 2, it might, so let's say the magnitude of vector 1 is 10 meters. So the magnitude is 10. Okay, let's forget about the units right now. And here the magnitude is 20. So if this worked like algebra, it would say that 10 plus 20 would give us 30. At least the magnitude will be 30. But this is wrong. So this is not technically wrong, but this will be wrong in most of the cases. We can't be sure that this will always lead to 30. Um, Actually, the range of this will, in terms of the magnitude only, will be actually from 10 to 30. So this is the actual range. So the magnitude will actually be in a range. So it will belong. This will belong to this range, on and which depends on the angle. So now let's talk about why. So that's the important question right now. Suppose let's take some vectors, and it will be much more easier. Suppose, think about that you have a ball. I think this is a pretty clear demonstration that I'm about to show you. Think of you have a ball, and you have ropes on some sides of it. Suppose there is a rope which I'm showing right now. Maybe I should increase the size of it to make it much more visible. And I have another rope which I will actually rotate right now, and I keep it like this. And this is the rope 1, so let's call this R1. So that's my rope 1. Let's actually use another color. Let's use white. Let's say this is our rope 1. This is our rope 2. Suppose I applied a 10 Newton force in terms of magnitude in this direction, which is represented by the arrow. We know force is a vector, so it will pull 10 newtons over here. Think about it, another force, 10 newtons, pulls it on this direction. Since they are exactly 180 degree apart, so that their angle between them is 180 degrees, what do you think the net resultant will be? Or if you have to represent the outcome, how can you represent the outcome of this case? Think about it. If you have a ball, you have two ropes, you pull them equally. Will the ball move at all? Of course, it won't move at all. So this will remain at rest, right? So this will remain at rest. So if I had to represent the resultant of this thing, I could basically see this case is basically as saying this has no net force. So basically, this cancels out with this. So right over here, if you actually check it out, the force one, let any one of them be force one, and the second force actually leads to a net zero force or zero vector. So you would get a zero vector even though you're adding them. So what did you, so we expected to get a magnitude of 20 newtons, but we actually got zero. In another case, so let's take another case. Let's copy this to make it much more quicker and easier for me. Let's take this case. Now we are gonna rotate this so that it's on the same direction. So it will be on the same direction, and still both are of 10 newtons. So we are still gonna keep 10 newton force on both the ropes. Now think about it. If you pull both the ropes in a single direction, you would assume that this will move in this direction. So what do you expect? This will not be in rest, which means the magnitude of the force, suppose the one force is F1 and another force is F2, will give you the magnitude, it'll be 20 newtons in this case, which is quite different from the 0 newtons that you would have expected. So this actually turns out, if I have to find the resultant, the magnitude of the resultant, this will be 0 newtons. So it's basically like no force is acting on this. Whereas in this case, it looks like a new force of 20 newtons is acting on it. So we saw two forces. The magnitude of these forces were same in both the case. The only thing that changed was the angle between them. And this is what causes vectors to not add algebraically. So that's why, so what I showed you, we did this calculation on the basis of a diagram. So I showed you a diagram, I showed what happened, and we guessed. So which means you must do this geometrically as well, or you can also do it factorially, which we will learn in a later video. So also this point, we can only like vectors. So like vectors are the vectors which are parallel in the same direction, so they are pointing in the same direction, which means if even though or even if this was not 10 newtons and some other force, it will still be okay. So finally, let's talk about what we are going to discuss and addition and composition of vectors. Of course, we are going to discuss something more on this. So let's talk about that. So if if we have to add only two vectors, we can use either triangle law or parallelogram law. However, we may not have always two vectors. However, if we have to add three or more vectors, we have to use polygon law. So another question that you might have are, what are these laws? So what is the triangle law? What is the parallelogram law? We will learn about them in another video. But before that, let's learn why is finding the resultant so important. It's important because it helps us to visualize much more clearly. So let's think about it. Let's take two cases. Let's take the same ball. Um, so let's take this ball and another ball. Both the balls are same and are facing the same condition. Think about it. If there was a ball that I said was moving, so this was the velocity vector, and if you can see the arrow, you will see where it is pointing, and it's what, suppose, let's say 20 meters per second. This is very easy to visualize, right? This is very easy to visualize where the ball is going to move. It will obviously move from over here. I'm only writing the magnitude in this case, but think about this ball and think if there were multiple ropes of shorts that were acting along them. So like this, I'm going to draw a lot of them to make it much more clear. So let's make a lot of different velocity or forces that are acting on this ball. So think about it. If I had a ball and I had this case where it isn't that easy to tell where the ball would move. Of course, as we know that that I'm assuming is this, all these components actually just go off to this, which means this will be the resultant. So think about it. If you had so many velocities, this is very hard to map out what will happen to the ball in the next second, let's say. But in this case, it's much more easier since there is only one thing that you have to care about. This is why resultants are very important. So in the next video, we are gonna do a question. Till then, bye bye.